Hello everyone, I am P.S. Datti, former faculty at TIFR Center for Applicable Mathematics, Bengaluru. Professor Nankumaran of Department of Mathematics, Indian Institute of Science, and myself are giving this first course on partial differential equations. Professor Nankumaran has already explained in great detail about our plan in this course, in this video course. Essentially, we will be covering many chapters of our recently published book on partial differential equation that Professor Nankumaran has already shown you. Apart from that, normally when we have given such a course in the classroom, we have not bothered to say anything about the prerequisites, essentially multivariable calculus and some analysis. But in this video course, since students might come from very different backgrounds, we have tried to list a number of topics from multivariable calculus and in some other things that are required in the study of partial differential equations. So, I urge you to again go back to your multivariable calculus course and try to refresh your memory so that they are not only useful in this video course but in your future study on partial differential equations. So, partial differential equations, they require lots of tools from other branches of mathematics, especially analysis, differential geometry, and the demand is so much, even new topics like distributions and other things are created for the purpose of analysis of partial differential equations. Apart from that, partial differential equations essentially arise in all branches of science: physics, chemistry, biology, engineering, and the interaction between these sciences and this part of mathematics have benefited each other. This interaction has enriched both mathematics and also the other sciences. Especially you might have heard that now there is a discipline called mathematical biology, which concentrates on population models and even epidemiology models, and they are all either ordinary differential equations or partial differential equations, and thus the analysis of partial differential equations become very important in the study of such topics. So, though we have chosen some simple topics from our book, so obviously in such a short course we cannot cover the entire book. There are many topics in the book, but nevertheless it is important for you to follow it seriously and work out all the problems and all the details in the theoretical part also from our book. Okay, so with this thing I begin my lectures, and today's topic is first order equations. So when we say equations, it is always a partial differential equation. So you have already heard Professor Nankumaran speaking about this first order equation in great detail, confining to two variable case. But most of the ideas and tools are already there. So what we are going to do in couple of lectures, we are considering equations in more than two variables. So it's essentially the same as the two variable case, except for some more equations and more algebra, more computation. Okay, so it's only that kind of work. I want to stress here one point. The first order, the study of first order PD, this is important, and this also brings in a subtle difference between PD and ODE. The study of first order PD essentially reduces to study of system of first order ODE. Okay, so I want to stress this point. And this part, the study of first order ODE, is quite well established. So we have, for example, existence, uniqueness, results. Whether it is one equation or system of several equations, these results on existence and uniqueness are more or less the same. Okay, so that's, but here we are considering first order equations only. Okay, and we do not have the luxury of extending it to first order system. Whereas in the case of ODE, if you study one equation, the same method works for a system of first order ODE, but here it does not work. This passage does not work. Okay, so I want to highlight that. Okay, so the first order study of first order system of PD is very complicated, and still there are many things to be known. Okay, for example, here, so any higher order equation can be converted to a first order, a system of first order ODE. So hence, once we know the existence result for a first order system, So we know at least existence uniqueness for ordinary differential equations of arbitrary order. So for example, here we cannot even just go from first order PDE to second order PDE. That also you see in this course. So the methods for example second order PDE are so different from the one we study for first order PDE. So let's fix some notation. Once we fix the notation, so whatever you have learnt in two variable case just carries over, and there is absolutely no difficulty. Okay, so first let me write a general first order equation. In n variables. Okay, so just in n variables. Okay, so we denote a point in Rn by x1, x2, xn. So standard notation. Rn, okay, and we use for the unknown function u. So this is a single equation. Okay, let me just stress that single equation. Interchangeably, we also use z. Okay, so this is a function of x. So in some textbooks they also use z. Okay, then for the derivative, so now since u is a function of x, u has n first order derivatives. So let's call that as p1, p2, pn. So in case of two variables, we denote the variables were denoted by xy, and instead of writing as a vector, we used p and q. P for the x derivative and q for the y derivative. But here, since we are dealing, so n is at least 2 because it's a PDE. So this pj is del u by del xj. So with these notations, so a first order general first order equation is of the form f. So it depends on x, u and p equal to 0. In some domain, open set, open connected set, or just open set, okay, for the description is not essential, but it's at least an open set, so that the derivatives and other things make sense. It could be whole of Rn. Okay. So as we have already seen, even in the case of ODE, even in the linear case, we cannot write a general solution for such an equation. Okay, that's ruled out. Okay, so even for ODE, okay, that's how the analysis of ODE started, and then analysis of PD also started. So just giving an equation, so this is first order because we are using only the first order derivatives. And then we will see further classification into linear, quasi-linear and fully nonlinear, just like in two variable case. Okay, so there is absolutely no difference. Okay, so basic problem and important problem even for ordinary differential equations. So always a PDE is associated with a Cauchy problem. So we should be able to solve Cauchy problem, or also called initial value problem. So it always comes with that. So we should be able to find always a method to solve such a Cauchy problem. Okay. So for that thing, we need to prescribe an initial value on the solution. So this u need to satisfy certain given initial condition. But in this setup, n variable setup, where should we prescribe the initial values? That is the first question. So once you understand the statement of the Cauchy problem, then it becomes easier to adopt the method of the two variable case and do analysis. Okay, so that is the next question. Where do you prescribe the initial condition? And that constitutes the Cauchy problem. So again, let's go back to the two variable case. So omega is in R2 now, an open set, and there we described the initial condition on a smooth curve S. So omega now in R2 and S, a smooth curve in omega. Okay. And the requirement on the curve was it should be transversal. Okay, so here we get a different terminology, but it is it's a transversal. Now let me come to that little later. So maybe just that. Okay, and then we prescribe data, initial data on S. Okay, then the method of characteristics we follow, method of characteristics, etc. in order to analyze the solution and also prove the existence and in some cases uniqueness also of the initial value problem. So here just you count the dimension. Omega is in R2 and S is a smooth curve, so it's one dimensional less. So this is just like a line. So this is two dimensional and this is one dimensional. So similarly, in case of n dimensions, in case of Rn, Okay. So we prescribe data on an n minus 1 dimensional surface. So this has already been explained to you in the preliminary topics, but it's also a good practice again to recall so that you see in the context of PDE. Okay, so once we understand this, the notion of n dimensional one surface, then it's easy to formulate the Cauchy problem. So let me just recall. So a very convenient way of describing the surface, parametric representation. So this actually is part of classical differential geometry. Presentation. So again, omega is an open set. And V in Rn minus 1. So one dimensionless open connected. So we don't want to consider union of, for example, two balls. Okay, just a single thing. And so again I write that I cannot write in n dimensions, so just again write omega here, and I want to define a mapping. So this is in Rn minus 1 V. So this is part of Rn minus 1, and this is in Rn. Okay, so I want to define a mapping. Okay, so here there are the variable we denote it by S1 Sn minus 1. Okay, and since we want to go from Rn minus 1 to Rn, so we need n functions. Okay, so Hi are from V to R. So we need at least C1. They are all C1 functions. Okay. So I want to say that the image of this so you collect all these points. So the image. So this set, yes, let me. Okay, so this is just set of all Hs. So again, let me call it. So this is H1s, Hns, n components. So this is in Rn as S varies in V. Okay, so this sits in omega. Okay, so this is a subset. So I take the image of all these functions. That's what I am doing here. Just image of this set V. Okay, that sits in omega. So you want to say that this S is n minus 1 dimensional object. Surface, we want to call it. Okay. So what conditions on H1, H2, Hn imply that this object is n minus 1 dimensional and not lower? It cannot be more because it's only in Rn minus 1. Okay, so you cannot expect it to be n dimensional. So it can be lower than n minus 1. So but what qualifies it to be called an n minus 1 dimensional surface? Okay, let me just explain that. So again you fix one S naught, so call it S naught 1, etc. S0 n minus 1 in V you fix it. And now you just fix all the components except the first one, So you consider a mapping from J to J S02 let me S0 n minus 1, and the requirement is that as J varies, so this point should vary in V so that I can operate H on that. Okay. So this is now one dimensional curve. Okay, so you have again omega. Okay, so this is HS0. Okay, and now I am just passing a curve. So this is the curve. Okay, and again from calculus we learn that the tangent vector to this curve is given by del H1 by del S1 at S0, of course. Let me not repeat it. S1. Okay, so sometimes I write it as column vector, sometimes row vector. So, but it's so a vector in Rn now because there are n components. Okay, but the partial derivative is only with respect to S1 because we are varying only the first coordinate. And now you repeat it for all the other variables. Repeat for other variables. This process, and we get, so del H1, the tangent vectors, they are in different direction. Sn minus 1, there are only Sn minus 1. These are all vectors in Rn. Okay, so that's, you remember, they are all in Rn. And how many are there? There are n minus 1 vectors. N minus 1 vectors in Rn. So here comes the definition of the hypersurface or n minus 1 dimensional surface. Okay, so S is called a hypersurface or n minus 1 dimensional surface if the above n minus 1 vectors are linearly independent. So that is the requirement on the functions. So that obviously such requirement depends on the functions h1, h2, hn. Okay, so those n minus 1 should be linearly independent, and thus these vectors span the tangent space to S at HS0. Sometimes we just write S0, actually it's image of, so tangent space to S. So let me just show you that. So here, so these vectors are in different directions. Okay, they form the tangent space. So it's very difficult to draw the figure, but you can just in 2 dimensions and 3 dimensions we can try that. Okay, so these n minus 1 vectors should be linearly independent in order that S to be called a hypersurface or n dimensional 1 surface. It's also called a manifold. Manifold is a more general object than surfaces. So surface is an example of a manifold, but manifolds are more than surface. Okay, locally they look like a surface, but S is also called a manifold. N minus 1 dimensional manifold. But manifold is a more general geometric object. Okay, so different terminologies. Okay. So once we understand what a hypersurface, so just when we say surface, hereafter it means only n minus 1 dimensional surface as far as first order PD is concerned. So now we can state the Cauchy problem and then try to analyze it. So all these things are done in 2 variable case. So I just recall them, and it's more like a copy and paste feature. Okay, so we will first what we will do in the next class. So this condition of the n minus vectors being linearly independent this is more algebraic, and now we state this in analytic terms, and then we go for the statement of the Cauchy problem. Thank you.